we are going to talk about rational exponents. What does rational mean? A rational number is like a fraction. A rational number is anything that can be written with a top number and a bottom number that are both whole numbers or integers. So rational numbers are things like 1/2, 3/4, -2/3, but 1/√2 is not a rational number. √3 is not a rational number. So rational exponents are exponents that are fractions. And remember that any whole number exponent, so something like 2 to the power of 3, that exponent, you could always think of it as being written over 1, so technically that is a rational number as well, so that's something it'll have in common. So a rational exponent can be written like x to the power of a over b. So what does this mean? So the power of a is the same as what it's always meant. If you had x to the power of a, it just means x times x times x times x, a whole bunch of times, a times. What happens when we add over b? The over b, well, we've just taken care of the a parts. This would mean that all of that is to the power of 1/b. Okay? A fractional exponent is actually comparable to a square root. So the square root, we have over here an example. X to the power of 1/2 is the square root of x. So what we've written here with x's to the power of 1/b, we could write as the bth power, that sounds weird, the bth power of x to the a. And that's what we have written over here. When we're dealing with these rational exponents, if we choose to write it as a square root or a bth root or a third root or a fourth root, we're writing it as a radical. So whenever we start adding these square roots in, we're calling it radicals. But all of the rules we have are the same as they would be for our regular exponents. So if you have x to the 1/2 times x to the 1/2, well, when we multiply exponents, we add, when we are multiplying the whole thing, we add the powers. 1/2 plus 1/2 is 2/2, which is 1. Okay, let's do some simplifying. I think I'll need more space. So the first example here is the fourth root of 16 to the power of 3. This looks pretty complicated. We could rewrite it as a rational exponent. Try to make it a little bit easier. So the fourth root is the same as to the power of 1/4. Now we have exponents that are multiplying. We have a power of a power, so that means we multiply the exponents. Now what can we do with it? Well, we could do 16 to the power of 3. That's going to be a very big number. I don't really want to do that. Sometimes it's better to make it smaller first. So this to the power of 1/4, it'd be nice to deal with that first. Now there's a nice property if you had x to to the 1/2 squared, because we can multiply the exponents, this would give us x to the 2 over 2. Very similar to the example we had over here. Pretty much the same thing, just written a little different at the beginning. To the power of 1, and we were able to get this all to cancel. So if we can write 16 as a base to the power of 4, we'd be able to cancel this. Let's see if we can do that with 2. So 2 to the power of 2 times 2 is 4, times 2 is 8, times 2 is 16. Perfect. We were given nice numbers here. 2 to the 4 is equal to 16. We still have the 1/4 because we haven't used it yet. Whew, we still have the 1/3. We haven't used that yet. So now these exponents are going to cancel. So I'm going to write out probably more steps than you usually need to, just so you understand the logic behind what's happening. So we have 2 to the power of 4 over 4, because 4 times 1/4, we'd multiply the numerators, we think of that as 4 over 1, 4 over 4. To the power of 3, which is 2 to the 1 to the power of 3, which is 2 to the 3, which is just 8. That one simplified very nicely, didn't it? Okay, next question. So we have a to the 3rd root squared and a to the 3rd root squared. Okay, so what can we do? A couple of approaches, but I think the easiest thing is to switch it into rational exponents, and we can use the exponent laws. So we have the 3rd root of a, which is really a to the 1/3 squared. And the second one is the exact same. So a to the 1/3 squared. What exponent laws do you want to use first? It doesn't really matter. We could multiply the big parts together and then do 2 plus 2, but I think I'd rather have this as a single fraction first. And then we're going to add the exponents. 2 plus 2 is 4 over, whoops, I almost wrote over 6, that's silly, over 3. Is that simplified? Yeah, it's a bit nicer than we had at the beginning, not a huge difference, and it would be acceptable also to write the 3rd root of a to the 4. Okay, final question here. Has some rational exponents and some radicals, lots here. Let's see what we can simplify. So I'm going to rewrite it a little bit better. When you're typing, sometimes it's very difficult to write a fraction. So 4th root of x to the 3. So the 4th root is to the power of 1/4. So the power of 1/4 times 3 is 3/4. And in the denominator we have y squared and x to the 5 over 2. Now, we can really think about this as this part goes together and this part goes together. I know it's all on the same fraction, but we would still be doing multiplication of the fractions, and it would all work out the same because we'd multiply the numerators, we'd multiply the denominators. So I'm going to think about it like this. I'm going to work on the y's first and then the x's. So for the y's, remember that the law here for exponents would be a dx over a to the y is equal to a to the x minus y. So here, same thing, 1/2 minus 2. And similar for x, we're going to do 3/4, subtract 5 halves. Okay, 1/2 minus 2, that's 2 would be 4/2, so minus 3/2. And x is 3/4 minus, maybe I'll write this over here, 3/4 minus 10/4 is -7/4, okay, -7/4. Okay, now sometimes a question asks for only positive exponents in the end. If this asks for just positive, then the negative needs to take the reciprocal, so it'd be 1/y to the 3/2 times 1/x to the 7/4. You could also be asked to sub in a value at this point. There's lots of different things that you could be asked. So solving question. If m is equal to 5 and m times square root of 3 is equal to the square root of 3q, find q. So we know a value for m. My rule always is sub in what you know, solve for what you don't know. So let's give that a try and hopefully it'll work. So we're going to put 5 in for m. 5/3 is equal to square root of 3q. So the brackets before around the 3q meant that the square root applies to the whole thing. It can help to clarify just in case the notation isn't very clear. Okay, so if we want to find q, what can we do? We have a square root around it. We're trying to get q by itself. We need to get rid of the things around q. The opposite of square rooting is always squaring, so why don't we square both sides? So now on the left side, it can be a little bit confusing. What do I do with this 2, with the 5, and with the square root of 3? So you can always go back to a simpler concept. So squared means times itself, so let's just multiply it by itself. And here the squared on the right side is going to cancel out with the square root, leaving just 3q. Okay, on the left side, we have a 5 times a 5 is 25. The square root of 3 times the square root of 3, which is equal to 3. We can divide by 3. So q is equal to 25. How do we know that we're right? Well, it never hurts to do a check. We should be able to sub q in the original equation, and it should work out. So the original equation was 5/3 is equal to the square root of 3q. Okay, on the left side, sometimes for a check, if you want to be technical, what you want to do is not have that equal sign because you're trying to show it's true. So left side equals right side equals. Okay. Square root of 3, square root of 25, which is 5/3. So left side is equal to right side. If you're doing a formal proof, then you should separate it like this. If you're just doing a proof for yourself, I wouldn't be as worried. And we found the value of q. So remember, this general rule we can use with linear, with quadratics, with so many things. Sub in what you know and solve for what you don't know.